So we've taken sensitivity and specificity of a specific test and used it to create a contingency table of possible outcomes for a made-up sample of 100,000 people. It's time to actually apply this a little bit. So our first question is going to be, awesome, we have this rapid screening test. A lot of people seem to be getting positive, so the question is, if you get a positive, what are the chances that it's a false positive? Now, there's one thing that you should take out of these conditional probabilities. It's the fact that when I say false positive, that could mean a couple things. Let's be a little more specific. I want to know, if you get a positive, what are the chances you don't have HIV? So to answer this, we need to go ahead and set up our probability here. Once again, I want to know, if you got a positive, what are the chances you do not have HIV? So we'll call it HIV complement, the opposite of having HIV. When I set up this probability here, I'm narrowing it down to if you get a positive, which means up on the table, I need to find the total number of people who got a positive. I can find that by taking the positive row, tracing it across to get the total number. So that is, according to my made-up sample of 100,000 people, 3,158.22 of them would get a positive. Now, out of all those people who got a positive, I want to know what percentage of them didn't have HIV. So, tracing it across here, I need to find the number who don't have HIV. That value is going to be right here. So that number will go on top. 2871.36. Dividing this off then, we're going to get 0.9092. Take a second, look at it. This should strike you super weird. This is, if you get a positive on this widely used HIV rapid screening test, there's actually a 90.92% chance you don't have HIV. Literally. Out of all these tests we're getting positives on, 90.92% of them look like they're false positives. And that's a really high rate. And while yes, after you get the first test, you're given a second, more accurate test, we can't help but think, well, let's say you do get a positive on an HIV test. Even though you might know 90% of those are false positives, that's probably not going to cure the fact that you feel really, really worried about it. So the obvious question to ask then is, why do we get this? It doesn't look accurate at all. And to answer that question, we're going to go ahead and reverse it. We're going to ask, okay, you go in, you get a negative, what are the chances you do have HIV? Doing this probability here, we want, once again, if you get a negative, what are the chances you do have it? Using these numbers then, I look across and I notice that there are a total of 96,841.78 people who got a negative on the test. And out of all of those people who got a negative on the test, it looks like, looking across once again, I have 13.14 of them who actually had HIV. And once again, just to make sure we're on the same page here, I'm looking at this row right here. These are all the people who got a negative test result. So out of the 96,000 who got a negative, 13.14 of them had HIV. Turning this into a decimal, we get 0.0001. And what this tells me then is there's a 0.01% chance that you actually have HIV if you got a negative. This is really important to realize about medical testing. When we're testing for a contagious disease such as this, we're really worried about this specific thing. That is, if I tell you you're not HIV positive, if you get a negative on that test result, you might engage in different behavior than if I told you had a positive. So we want to be really careful that we're telling people negative only if they don't have HIV. That's why this percentage is so low here. That is, if I tell you you're negative, there's only a 0.0001 or 0.01% chance that you actually have it. Now, in order to be very accurate with this, in order to be very careful about telling people that they're negative, I tell too many people that they're positive, which is why we have this really large false positive rate on this test. In conclusion, sensitivity and specificity give us a lot of information about medical testing, and this applies to things such as drug screening when you go to a new job, as well as testing for things like HIV or Down syndrome. Understanding what sensitivity and specificity tell us is important, and being able to deduce other things based on that is equally important, such as what we've done here with detecting how many false positives we get. In addition, it gives us an excellent example to explore this idea of conditional probabilities.